All right, so today we have midterm review, right? And by way of review today, I want to ask you a question, and we'll talk about it for essentially the whole class period. What could be on the exam? Okay, so what I want to do today is, so I have a list of potential topics that we've covered. I will post this list to Canvas after class, okay? So you will have this list, and attached are some exam tips, which we'll discuss at the end as time allows as well. But actually, I'll make sure that we have at least a few minutes to talk about this, maybe 10 minutes or so. Then I'll post this to Canvas, so you don't have to worry about, scribbling everything down. And the main point here is just as a reminder of all the ground that we've covered, and which could be, which I could possibly ask you about on the exam. Also, kind of as a study guide of sorts, right? If there's something that you had forgotten about, right? Because we talked about it in week 2, or you remember that you had difficulty with, then, from the list that we're going to go over today, and that you'll see posted to Canvas, then that's a good reminder of things that you should be taking a look at. So if there are no other questions to get started, I'll ask you this question. Yeah, Francisco. We have extended office hours tomorrow. If you come by, I'll stay with you after the official ending of office hours. Yeah, that'll work. Okay, any other questions? Okay, great. And all of you've made it this far in the program, so you're doing all right in chemical engineering to have made it to your junior year. That goes for everyone here. I know it may not always feel that way, but you really have been through a lot to get to here. So let's get you to next semester. All right. So what could be on the exam? Any volunteers? Topics that could be on the exam? Yeah. Fluid statics. We'll get to momentum balance for sure. I want to start with, I want to expand on this topic. So fluid statics. There's a lot more. Sorry, what manometers? Yeah. Right. So if we have, some thing like this with, some kind of a pressure, some kind of a fluid height in here, it can tell us something about or some kind of a fluid height, it can tell us about the pressure inside of a container or something, right? If we have multiple fluids, then we can figure out the pressure contribution from those multiple fluids using the fluid statics expressions. Or expression, right? Delta P is minus gamma delta Z. All right, what else? Fluid statics. Let's discuss other things from fluid statics. Wait, what's this? Weight on a fluid. Weight on a fluid as moving. I'm actually not sure which one you're talking about. You can come up and draw if you want. Okay. All right. Well, Francisco's coming up and going to sketch. He's going to sketch a problem for us to discuss. Other topics in fluid statics that we have. Yeah. Surface tension, right? Right. So surface tension. So if we have drops and bubbles, what is the influence of the tension on the pressure that's inside? Yeah, so this is an example of where we had a fluid.
It's like a fluid in between box and some plates.
Mm-hmm.
Like what would the velocity be if it was moved at a certain point?
Right. And this is actually an example of a momentum balance problem, right? So this was a case that was moving, right? That's why maybe I was a little bit thrown off. This is something where it was moving. Yeah, but this is a good one, right? So this is where it was moving and we had to find a force. So if we're finding a force, what kind of balance are we going to use to find a force? Thank you, Francisco. What kind of force are we going to use? What balance? Momentum or mass balance, right? If we have this. I'll write that down. Let's come up now twice. right? So momentum balance, which was the main way that we would address this problem. Surface tension, manometers. What else do we have from fluid statics? Capillary action, right? So that's related to, the wetting behavior of a surface, right, as well as the surface tension. I had a hand back first. Yep. Okay, yeah, so that was when we were, so you're talking about the section where we developed we looked at the pressure on a fluid element that was triangular. The main concept to take away from here is that pressure is a point property. Pressure is a scalar, not a vector. And so that 1/2 came from the fact that we have this triangular face, but that was not a general rule for, for an arbitrary fluid element. We were just showing that pressure is a scalar. Okay, so that is another important concept. So, sorry, Francisco, I'm going to erase your fluid. So we have pressure is a scalar. And Francisco, you had another comment. Yeah, if I were asking you a question on contact angle, I'd give you a contact angle. Yeah, I'd give you that as I try to give you as much information as I can. And if not, try to rely on the tables in the back of the book, back of your textbook. Yeah, so capillary action based on contact angle. What else do we have? Yeah. I would not expect you to derive and show that pressure is a scalar. So I did get a question of, would I expect you to derive something on the exam? And for something like this, no. I mean, we've gone through some derivations in class that are fairly complex. But I will sometimes ask you for an answer in symbolic form. So that's like an answer to a specific fluid problem in symbolic form. So if you consider that a derivation, then that's the type of thing that I would expect you to do. But this kind of like general physical principle, no, that's not something we're going to cover. Okay. What else for fluid statics? Yes. Multiple fluids, yeah. So related to manometers, right? If we have multiple fluids, we have biodiesel floating on water or something, right? Then we know how to handle that from our fluid statics. Hold on one second. This thing is still not fixed, so I can hardly hear. Yes, what? Varying diameters. Yeah, so what about varying diameters is tricky when we get to fluid statics? The pressure, what's that? The pressure, that's the force. So pressure is the force times area, right? Yeah, so pressure is a force over an area, right, per area. And also remember, we saw that a consequence of delta P is equal to minus gamma delta Z. This only depends on Z, right? So, we saw like for example, a YouTube video, we saw an extreme consequence of this, that the change in pressure within a fluid is only a function, if we're within a single connected fluid, the change in pressure is only a function of the elevation, right? Not where we are laterally or even the shape of the container laterally, right? The force would depend upon the area, but the pressure would not. Okay. So another thing that we have to keep in mind here, and it's just a point that we want to be careful of, is the sign convention, right? So we had that delta P minus gamma delta Z. This is because by convention, we have pressure acting inwards on a fluid element, right? Pressure goes up as we move down within a fluid. You can feel that pressure on your ears if you're in a swimming pool. Pressure acts inwards on a fluid element, and that's where this negative sign came from. So make sure to keep track of that. I uploaded 3 new videos of example problems over the weekend. One of which is me going through a manometer problem, following through 5 points or something through the problem, and applying this rule as we go. Yeah, sorry, question.
So if you had a manometer with different size tubes, like one has a bigger diameter or whatever, then does that mean the pressure is the same at each elevation?
Yeah, that's a good question. So if we had, let's say we have a manometer like this, not even really a manometer, just a U-shaped tube filled with one fluid, right? So how does the pressure here relate to the pressure here? It's the same, right? They're at the same Z, but the area is different. And so, yeah, the force that's, in this case, if it's open, they're both at atmospheric pressure, for example. And the force that the atmosphere is exerting on the fluid column in this space, right, would be larger than the force that the atmosphere is exerting on this space, right? Because the force would be the pressure times the area, and this area is greater. So even though the pressures are the same, the force that's pushing down on the fluid column, right, from atmosphere, from all the air that's above us, would be larger here than it is here. Yeah, Michael.
In cases like the fluid statics, when we have a gas, you want us to assume ideal behavior where the pressure is the same throughout the fluid, or we want us to
if I want you to consider the variation of density with elevation, as we did for an atmosphere or something, I will specify that's what I'm asking. Outside of this class, you'd have to ask, is the pressure variation across the height that I'm considering significant enough to cause an error in my calculation? Right. But here I will specify if you have to include the variation of pressure over height. Okay.
Right.
Does that answer your question?
I think one problem on the homework where we had some gas that goes in the closed off and the sometimes, and you have to assume that behavior to that gas.
Oh, yeah. So because you were compressing the gas within that chamber, yeah, in that case you would have to assume ideal behavior for a gas, right? And state your assumption, right? Yeah, so state your assumption. Okay. Anything else on fluid statics? Okay. Yeah. So surface tension, how surface tension gives rise to pressure difference across a curved surface, right? So we had some expressions for delta P depending on radii of the surface, that kind of thing. Right. We had different expression for a sphere or a cylinder, or a surface of arbitrary curvature. Yeah, so I get it was on the slides. I expect you to have that ready to go. Yeah, the slides are kind of the ultimate arbiter of what we've covered in this class, right? What we've discussed in lecture, in general, is the ultimate. Is really what we're discussing today. Yeah. Okay. I put the equation on the slide, so yes. Yeah. Okay, one other concept that came up, I believe just on the homework, but I just want to make sure that we cover, because it does come up in real fluid problems, is absolute versus gauge pressure. So we are now covering it in lecture. So what do I mean by absolute versus gauge pressure? Someone explain. Yeah. Yeah, so absolute. Yeah, so absolute is whatever pressure you have plus atmosphere. So it is like an absolute pressure where zero pressure on an absolute scale is nothing there, right? Gauge is relative to the atmosphere, right? And this comes from this nomenclature comes from the fact that if you have a pressure gauge, there's often a differential pressure gauge measuring pressure, for example, in some vessel relative to the surroundings. Okay, so it's absolute versus gauge pressure. Okay, anything I'm missing on fluid statics? Okay. So some chapter 1 topics, and then we're going to spend the rest of the time on our balance equations. So in chapter 1, someone give me an example of something from chapter 1 that we've covered in class. Sorry. Chapter 1 is the first chapter, the first couple of days of class, and really just intro. Natalie. Dimensions and units, right? We've covered dimensions and units. And I'm going to say dimensions not equal to units. If this doesn't make sense to you, I'd say go back and review. So dimensions are not units, but you should understand what both dimensions and units are and how to deal with them. What else from chapter 1, early going? Yeah. Viscosity. Newtonian. Non-Newtonian. We have not gone over calculations with non-Newtonian fluids. So meaning that would not be fair game. So we have, you know, our shear thickening and shear thinning, right? What else from chapter 1? Yes. Knudsen number. What is the Knudsen number? Yep. And what is it comparing? What is Knudsen number telling us? Right. So it's free path to size of a system, and it tells us whether or not continuum assumption is valid. Right. Right. So basically in chapter 4, when we're writing del dot v is equal to 0, this expression is really only true if velocity is continuous. Right. So this is only true if we assume that the space between molecules doesn't matter, which is true if we can make this continuum assumption. Yes.
Kind of question back to like the shear thickening, shear thinning. Will we need to know the alternative names for those?
Yeah. So I may sometimes refer to these, for example, as dilatant or pseudoplastic. Yes, that's right. Yeah. So alternative names, nomenclature. All right. Continuum assumption. Yeah. Definition of a fluid. Yep. What is a fluid? I heard a favorite topic. What was that I heard? Yeah, I know. What did you say? Okay, incompressibility, compressibility. Something that I promised that we would discuss nearly every day in class, but we haven't actually talked about for a few days of class. Reynolds number. Yeah. We will fix this in chapter 5. We're going to derive where the Reynolds number comes from by looking at Navier-Stokes equation, and it will guide a lot of our discussion from here on. But Reynolds number is a key concept. And in general, dimensionless numbers, right? We're going to talk about how to develop new dimensionless numbers. But just the concept of we have a number that can vary, right? Reynolds number depends upon the velocity, the fluid properties, the length scale that we're considering. So it's not the same for every fluid. It's not a single number that's the same for every fluid, but it doesn't have dimensions, right? It is dimensionless. Yeah, Francisco. How Yeah, so I would expect you to be able to, in general, tell what the shear stress is for a Newtonian fluid. We've gone over that several times in class, both for the, so we've looked at the case of flat plate now a couple of times, right, where we have a flat plate. So I expect you to know the shear stress relationship, as well as what this velocity profile is. And we also have a more general form, right? Since chapter 4, we have a more general form for what the shear stress in a Newtonian fluid is. Yeah, Tata. No, we're not going to consider a slip condition. Yeah. Yeah, so no slip was something that we discussed, I believe, in chapter 1. Okay. Anything else from chapter 1? For flow between the plates, we discussed in chapter 1. We also discussed last week, right? Okay. So moving on to chapters 3 and 4, right? So remember in chapter 1, we did some definitions. Chapter 2 was fluid statics. Chapter 3, we did mass, momentum, energy balance from the perspective of fixed control volumes. In chapter 4, we developed mass, momentum, energy balance for differential control volumes, right? So we let the control volume shrink really, really small. But we used basically the same approach, right, between chapter 3 and 4. So for our discussion today, I'd suggest we unify kind of what we learned from chapter 3 and 4, because there are some similar concepts back and forth. So momentum balance. What do we have on momentum balance? What did we cover? Yeah, so what is momentum? That's a good one. Right, so what is momentum? So other important concepts here, right? We have F is equal to M A, right? More or less, we've written this out for a fluid in 2 different forms, right? So we have the control volume form and the differential form. And for a Newtonian fluid, a Newtonian incompressible fluid, F is equal to MA becomes the force balance part of Navier-Stokes. So other things in the force balance or momentum balance are, and so actually in just a note of clarification, in class, you hear me discussing, sometimes I say momentum balance, sometimes I say force balance, and that comes from here, right? Because this is really a balance between forces applied and momentum of the fluid, okay? So that's really where that comes from. And this is telling us that the way that we change the momentum of a fluid is by applying a force. And if we apply a force to a fluid, we're changing the momentum. Okay. We have sign conventions. To be aware of in momentum balance. So remember, we have sum of the forces is sum m dot v out minus sum m dot v in for steady state 1D, right? So a sign convention, this was out minus in, because this was a balance equation discussing the force that we have to apply to that system. Other sign balances, remember in Navier-Stokes equation, we end up with minus grad P, right? And there's a negative sign that comes all the way back from that sign convention that pressure is acting inwards. That's where that thing came from, but there's a negative sign there. So review that. Another thing that we've discussed, just general concept, is advection terms. Right, so we discussed how fluid that's moving in both X and Y, right? So if we have a fluid that's moving in both X and Y, then this fluid can actually be carrying this fluid can actually be carrying x component momentum, x momentum, with the y component of its velocity, right? So we discussed this for the control volume form, and this also came up when we saw this in the differential form, right? Okay, and then in the control volume form, right? So for CV momentum balance, we saw 1D momentum balance. We saw, 1D or uniform. We also saw 2D or non-uniform. And the the recommended way to deal with these non-uniform inlets or outlets when we're doing a momentum balance is by using the momentum correction factor. Right. So non-uniform flow, yeah, so uniform, let's start there, would be if the velocity is just the same everywhere across the inlet or outlet. Non-uniform would be if we have some variation in the velocity across the inlet or outlet. Okay, so for example, parabolic flow or something. Okay, yeah. Yeah, it's because, so the that's why I prefer your textbook uses 1D. I prefer saying uniform. When your textbook is saying 1D, it means like if this is your inlet and this is your outlet down there, this is the one dimension and over which things in your system are changing. And then the second dimension would be the dimension across the stream. I think that gets a little confusing, so that's why I tried to supplant that with uniform and non-uniform as much as possible. This would be non-uniform flow, that's correct. Yeah. It doesn't have to be parabolic, right? And you've seen an example in the homework of some other kind of shape, something that if you plotted it would look like this. And we'll look at where that comes from actually in a future chapter. Okay, so control volume form, we have 1D, 2D. We have steady, right? Steady state assumption or unsteady. What happens if we have unsteady flow? And forces on solids cut by a control surface, right? So if we have remember when we had the vein that was turning the flow, and we drew our control surface, something like this, we were considering the force acting on this control volume, and so is acting on the control volume through that cut surface there. So another thing here, this is maybe just a tip, is try to make your control surfaces normal to the flow, right? It makes things a little bit easier in keeping track of inflows and outflows. And then in the differential form, we have Navier-Stokes. What assumptions did we apply to get here? And what do the terms mean? Right, so we discussed what the terms in Navier-Stokes mean. There's pressure term, the viscous term, the momentum advection terms, right? The convective derivative of momentum term, and so on. Okay, what else? Anything else in momentum balance? Yes. Yeah. So yeah, that's a good one. So shear stress, shear, and pressure are force per area. Because both of these things act, both shear stress and pressure act on the surface of a fluid element. And so these are both forces per unit area. That's correct. Yep. Yes. Where's the so in general, pressure is a response to fluid motion. So as a fluid is moving, the pressure will vary in response to that motion. And pressure can induce motion, right? So remember, so think about pressure as a force, something that's applying a force, or it's like an internal force within the fluid. So movement can produce forces, right? Right. So change in momentum can induce a force, and a force can induce a change in momentum. And so the pressure is like the internal force that fluid elements are exerting on one another. That can be a response to motion and can give rise to motion. Anytime we have a pressure, there is a force. I'll say that. It is in a force balance. Yeah. Yeah. Yes. There's an equation for momentum correction factor based on a velocity. You can find it based on a velocity profile. So you may have to integrate for the momentum balance, right? Based on the definition of momentum balance. That's correct. Okay. Other questions on momentum? Okay. So what else have we covered? Yeah. Bernoulli. Yeah. Let me find a board that I can use. So the Bernoulli equation. What about the Bernoulli equation should we know? Yeah. Right. When to use or not to use. So when would we use Bernoulli? Yeah, no work, no heat, no friction. Yeah. We often satisfy no work, no heat, but no friction is probably one of the bigger cases where it would be violated. Okay, but if you can assume no friction, then Bernoulli is fantastic. Yeah. And only use no friction if I explicitly state no friction. To neglect viscous forces. On the exam, yeah. I hate saying it like that because in real life, no one's going to tell you that you can neglect friction. But to be fair on the exam, I'll give you some hints. Yeah, so one way, so how would you know in real life to neglect friction? One way could be to try to include it and see if it's negligible. Another way could be, well, I've solved similar problems like this in the past and I know it's negligible. Another way would be if you know something about the flow and what we're going to learn later about how boundary layers form, and you know you're away from a boundary layer where the viscous influence is. So a little bit of experience and some trial and error would let you know when you can neglect friction outside this class. Yeah, Francisco. we'll discuss it more as well. I'm not just going to leave it up to you to figure it out eventually. We will discuss it more. Yeah, Francisco. No, we'll see. It's not just having to do with the surface roughness distance, but that's a topic for another day, not for this exam. Okay, what else do we have about Bernoulli? So another key concept here is relation to energy conservation, right? So Bernoulli is effectively a statement of energy conservation where there's no heat, no work, no friction. Right, so it's telling us about trade-offs within gravitational potential energy, kinetic energy, and the pressure available to do work within a fluid. Right, and we can trade off our energy among those three different forms within a fluid. Yeah, Stedman. Fantastic. I should have called on you first. Okay, anything else on Bernoulli? All right, so that brings me to energy. I guess we're going to finish with mass. But now for energy balance, and I do want to talk about some tips. So we're gonna list off some concepts here. So again, we have sign conventions, right? Sign conventions for heat, work, pump work, and so on, right? So be careful, mind your sign conventions in the energy balance equation. For the control volume term, for the control volume form of the energy balance, we had 1D, 2D, or uniform, non-uniform. And there was a correction factor. The correction factor for 2D or non-uniform inlets or outlets, that's different than the momentum flux correction factor. We had unsteady, right, versus steady. And we had an inviscid or versus viscid. So we had an inviscid form of the energy balance. Euler's equations were in the slides. And as opposed to the full form, which includes the viscous dissipation term. Right, so we had the definition of viscous dissipation term. All right, I had 3 hands up here. This was the first one I saw. Yeah. So correction factor is so you can use average velocity with a non-uniform velocity profile. That's exactly why we use the correction factor. I'm going to go in the order in which hands came up. Yeah. Inviscid. Yeah, sorry. And then I put parentheses here because we have both a viscid or a form that includes viscous term, the viscous dissipation term, and an inviscid form which neglects viscous dissipation. Francisco. Yeah. When or when not to ignore viscous work? When to ignore viscous work? Yep. And Michael. So formally we use V average, but to approximate Reynolds number for the purposes so far, because we have not rigorously defined it, any velocity that's characteristic of the flow speed is fine. So V max or V average would be acceptable. Okay. Yeah, and we'll talk about another thing about the non-dimensional numbers that we're going to cover in chapter 5 is a lot of times we're just trying to make an estimate, like an order of magnitude estimate. And so the difference between V max and V average, is not even a factor of 2, right? And that's a small error when we're discussing these kinds of non-dimensional parameters most of the time. Okay. Yep. We will occasionally use like Reynolds number to look something up on a chart or in a formula, and there you want to use the same one that it was defined for that chart or formula. But yeah, we'll use it to estimate kind of general fluid behaviors, and whatever you can use is fine. Okay. As long as it's representative of the flow. Yeah. All right. Other comments on energy? Okay, and moving right along to mass. Yeah, so so other topics, we had Reynolds, transport theorem, acceleration of a fluid particle. This is Lagrangian or Eulerian. Yeah, so sort of other topics from chapter 3 and 4. And we use Reynolds transfer theorem as our way of getting into the control volume form. We use the Lagrangian Eulerian as our way of getting into the differential form. So these are actually kind of analogous. Yes. You may have to look at the terms of the stress tensor for the Newtonian fluid, right? That's something that we discussed and that we've used. But I'm not expecting you to know like tensor operators, right? Because we haven't discussed tensor operators. Okay. Okay, so for a mass balance, again, we have, let's see, so for the control volume form, again, we have 1D and 2D. In 2D, there is no correction factor because it's we can just write our mass balance in terms of the average velocity. But how do you calculate the average velocity? So how do you calculate average velocity, mass, or volumetric flow rate? Right, so our volumetric flow rate is our average velocity times the area. And then if we multiply by density, we get our mass flow rate. We had unsteady and steady forms of mass balance. And we had the incompressible form. Of mass balance. Right, remember in the incompressible form, we just had the sum of VAs coming in is equal to the sum of VAs going out. And the mass part actually dropped out. Okay. And then for differential form. And we have a general form, right? That we highlighted in class as being sort of general for, you know, for example, for incompressible flows as well as compressible. And then we had the incompressible form. Right, which is part of the Navier-Stokes equations. And again, we can write del dot V is equal to 0. There's no density or mass in here, right? Because we have constant density and it dropped out everywhere. Okay. Even though this has no mass factor in it, it's still a statement of mass conservation. Yeah. Only the case for incompressible fluid, right? For a compressible fluid, this is no longer really that relevant, right? Okay. Any other comments on mass? Questions? In general, it's a good place to start a problem, right? If you don't know where to start, or even if you think you do, mass conservation will often tell you something else. Okay, so don't neglect mass conservation, even if you see it's a force or energy problem. Yeah. Yeah, less than 6. That's for sure. There's going to be three questions on the test. Yeah. I mean, the first one though is true false. So there's a few setups in the first one, right? Natalie. Yes. You're not going to be asked to solve 5 equations with 7 unknowns. We haven't covered integration of the other ones in there. So in the lecture, we just said we would do that at some point in the future. Yeah, Paula. I don't want to talk about the historical averages of average scores. I mean, the first year I told you it was too long, right? So average score was too low that first year. I mean, I'll say this for not to induce panic. I saw that induced a wave of panic in the classroom. That's not my intention. This is a core class, right, in chemical engineering. So I keep the average of the class in line with historical averages for the department in this class. So I don't want to penalize you for having me as your instructor. Yeah.
So that like midterms will be curved or
Final grades are curved.
okay, so we won't. Okay.
Yeah, final grades are curved. Yeah.
Okay.
So inclusive of all the things. Yeah. There's not a single equation sheet for the class. I do include information that you may find useful on the exam, like tables and things out of your textbook, as extra pages on the exam. Open book, open notes, and you can talk to me, right? You know, you can write out your own expressions or know where to pull them up. Yes. That's a question I can never answer, even to all of you. Regardless, no, absolutely not, never. Yeah, the head form, yes, could be on here. Yep. So head form is basically saying the energy within the fluid in terms of gravitational potential energy. So it takes the energy within the fluid and puts it in terms of the gravitational potential energy that fluid has. Yeah, dividing Bernoulli by gravity, for example. Yeah. And the units of that would, or the dimensions would be length. Yes. Okay, some general tips before. Okay, one more question. Yep. No, that's okay. Yeah, so policy on tablets and computers. I understand many of you have slides on PDF, textbook on PDF. Tablets and computers are okay. Internet is not. Okay. If it will keep you from opening up the internet, then do it. Okay. Because I absolutely do not want to see I'll be walking around and I'll be at the back of the room. I absolutely do not want to see internet on Wednesday. Okay. Okay. General tips until we get kicked out by the next class. True false questions are going to be on the exam. It's the way that I like to test concepts, right? But I am testing your understanding of concepts, not your ability to guess true or false. So most of the points are for the explanation, not for just getting true or false, right? So even if you know the answer is false, make sure you write out why, okay? Because most of the points on that problem are going to be for your explanation, not for just whether you get true or false. Yes? No, so the box would be just for the true or false, and then the explanation is in the area for the work. So I actually spend, so on Gradescope, I do look at the answers in the boxes, but I spend most of my time looking at your work. So that's another thing is we are using Gradescope. I understand that, so that means there's limited space, right, on each page to solve the problem. I understand not everyone can work it out in that amount of space, and that's fine. You can use extra sheets of paper, but tell me, or use the backs of the paper, but tell me where to find your work, okay? Because I will be hunting for it. Please try to make it easy for me, okay? Yeah. Test is a paper test. I will be handing out the paper test on Wednesday. You will be handing me back the paper test on Wednesday, and then I will handle scanning. Okay? So the test is a paper test in this room on Wednesday. So related to showing your work, and really, I want to see that you know how to approach the problems. That's the most important thing to me. So I would suggest that you look at the whole exam first, and write out solution methods, like what your approach would be for the different pieces of the exam before getting stuck on, or potentially stuck on one or more of the problems. Then return as you have time to those other pieces. If you don't know an answer, or you find yourself getting stuck, you're spending a long time, then I suggest you skip ahead. Maybe use a symbol. If you're solving for velocity, say, I'm going to call this velocity UA because it was the velocity from part A, and then continue on the problem, just to show me that you know how to solve those other types of problems on the exam. Okay. Yep. Well, you know what? I can't actually say that that the first problem is easiest and they tend to get hard, because it's going to be different for everyone, right? Some of you are going to find some types of problems a lot easier than others, so I can't generally say that. Yeah. So I'm really most concerned with you demonstrating your understanding of where of how to approach these problems and where it all comes from. And that's really what I'm assigning the most credit to as I go through this. So something like knowing that you should be using mass conservation to solve a certain type of problem tends to be weighted pretty heavily on my solution keys. So just stating, so sometimes just stating the approach that you would use if you had time to go through the problem, if you're running out of time or something, can actually net you a lot of points. Because again, I want to primarily know that you understand, or primarily know that you understand how to approach these problems. Does that make sense? Okay. There's a lot of math, but it's not a math class, right? This is a class about understanding, basics of fluid mechanics. Okay, yeah. Sorry, do I have what? I'm not going to make a promise there because I'm afraid I'm going to break it. So, yeah, in the past I've made that mistake. I will work on grading them as fast as I can. I have a big grant due on October 6th, so I'm going to be pretty impacted until then. I can tell you. I'm not sure. I haven't kept track of that. All right, final note that I have on here. Let's see. So list your assumptions, right? Anything that's given, as well as anything that's that you're going to state yourself. We discussed choose an appropriate form of the balance equation as general as you know applies, and then simplify. Draw your system, okay, and draw your control volumes and control surfaces. Final one, watch for significant digits. If it's especially egregious, that's when I start taking points off, but generally match what I've given you in the problem. Okay, that was really fast tips, but these will all be online as well.